Hello everybody, welcome back to ML Expert's large-scale machine learning section. This is the processing orchestration video. In the last data processing video, we saw how we could use Spark to create features out of these actions that customers have taken. We also saw how we could develop labels for those features, and we even saw how to join those items together if we wanted to create some sort of training set for a machine learning algorithm. Generally though, we don't want to just do that a single time. We could want to do that every 24 hours. This way, we would have a fresh daily update of different features for particular customers per day. The problem is, I don't want to do any of this stuff manually. It would be nice if we could have some sort of software perform a process for us incrementally or periodically, such that on the 24th hour of every day, we could get the interaction data from the search page, get the interaction data from the carousel that would be on the main page. This would house all of the recommendations that we have available. It would merge the interaction data into a single data frame. We saw that earlier when we went over the Spark code. And finally, it could join the interaction features with the labels to give us these training data. Again, we don't want to do this manually. It would be ideal if it could also handle data dependencies. So for instance, let's say we had a single file which would join the features in the labels. Well, that job couldn't actually begin executing until we've aggregated all of the features and we've aggregated all of the labels. And let's say those were in their own separate Python files that we're submitting to Spark. We have to make sure that whatever has to be done serially is done in order, and whatever doesn't can be done in parallel. Finally, we want this to be able to scale up. We were talking about the different jobs that we wanted to run for a single model, but let's say we had an extremely large interface for customers, different product pages, different search pages, different home pages, things like that. In that case, we could potentially want to run thousands of these processing jobs per day, and those jobs could even depend on one another, in which we'd like to be able to represent and make sure that it can be handled. So we're going to use a tool called Apache Airflow to manage this for us. Apache Airflow uses the concept of a DAG, which is a directed acyclic graph. So here is an example of a DAG, and the first thing that the DAG does, and they can do this in parallel, is get data from some location A, get data from some location B. This could be the search page, and this could be the carousel. Once it gets both of those data, it can join them, and then it could fetch data from some other location and then join those up to get the final result. So let's say these were the labels, so now we have all of the features and labels joined together, and this is what we can actually use to train our machine learning model. This is a very basic example of a DAG. Typically, jobs are far more complex. In order to show all of these DAGs and the previous runs of DAGs, Apache Airflow offers a web server for us. It's actually a Flask app. Flask is the same framework that we built our simple web page on. Now, this app allows users to trigger DAGs. It also allows users to browse the DAG history, and that is stored in a database. Another component of Apache Airflow is the scheduler. The scheduler monitors the database to check the state of each task within each DAG. It fetches different DAGs in order for those DAGs to be executed. It sends DAG tasks to an execution queue to be later executed by some worker. And then finally, it writes the DAG runs to the database so that we can see which DAGs ran, were they successful, and how long did they take to run. Now, the last component we'll go over is the worker. The worker pulls the task queue in which the scheduler sent the tasks to, it runs the actual task, and it stores the task state in the database so that the scheduler is aware of its progress. Let's go ahead and see a diagram of how this would play out. So here we have our user. This is our web server scheduler. This is a queue, all of the workers. This is the database, and this is the DAG store. So here, a user on the web server would trigger some DAG. The web server would fetch the DAG from the DAG store. This is typically S3 or some distributed file store. The web server would then schedule that DAG to be run with the scheduler. The scheduler would take all of the tasks in that DAG, figure out which ones have to be run serially or parallel, and submit them to the queue. Workers constantly pull this queue in order to consume tasks from the queue and perform the work. Now, as these workers are doing their work, the scheduler will periodically check in to see if the workers have completed the tasks. When the workers are done, they will say task complete. The idea is that the scheduler, monitoring the database to check if tasks have completed, will allow the scheduler to schedule subsequent tasks that had dependencies that had finally finished up. Now that the worker tasks have actually finished, the scheduler will enqueue more tasks, so the workers will pull that task again to get the serial task, do the task, update the database that they have, in fact, done that task. The scheduler will fetch more tasks, and finally, if all of the tasks are done in terms of the DAG scheduler, then the scheduler will add DAG history to the database. This will allow the web server to pull the database to check on the status of some particular DAG run. Finally, the web server will relay back to the user that, in fact, yes, a DAG run has completed, and the user will be able to check the stats of that DAG run, such as were there any failures, how long did it take, and perhaps maybe even alter the schedule of that DAG. So let's talk about some of the technologies that are behind each of these components. The workers are actually implemented through something called a celery worker. Celery ensures that if one of these workers goes offline, such as the host itself going down, or perhaps the host losing network connection, Celery will quickly adapt and assign tasks to other new workers to come and take its place. The queue is typically fronted by something called RabbitMQ. It supports a cluster of queues so that we can scale up the number of queues if the scheduler has a very high load to be scheduled, and it allows the queue to have a high availability. The scheduler is typically the single point of failure for Airflow, so in older versions we would need an active, passive, hot standby situation, which we've talked about in the past. In more recent versions, they support concurrency amongst the schedulers, so this means that you can have many schedulers running at the same time. They will ensure that tasks don't get scheduled twice by mistake. Now, moving on to the database, we'll have to have some active, passive, hot standby here as well. Now, moving on to the DAG store, that's typically in a distributed file store, so I used S3, and we'll go ahead and see a demo of that here shortly. And finally, the web server is typically going to consist of multiple instances behind some load balancer, such that if a single instance goes down, we can still schedule and view our DAGs because there's more than one host. So let's go ahead and see Apache Airflow in action. Alright, this is the Airflow web server UI, and right now I'm actually running this instance of Airflow on AWS. Both AWS and Google offer a fully managed Airflow service. Here we have our list of DAGs in this column here. Again, a DAG is that directed acyclic graph that we talked about earlier, and these DAGs are backed by Amazon's S3. So basically there's an S3 bucket with this file in it, and so if we click into this file, we can see that this is our very basic and simple DAG. So we have an aggregate search interaction, and we have aggregate carousel interaction, and that finally feeds into a join of the search and the cancellation data. Now, we could have organized this differently to have the cancellation data maybe here and then have all of them feed into a single join, but that's up to you and how you want to organize your individual tasks within a DAG. Ideally, what you want is for all of these tasks to be reusable across different DAGs that your team owns. All right, so how do we actually program or create one of these DAGs? Well, if we go over here and click code, it will pull up the exact code that's backing this DAG. Let's go through this quickly. So one of the main points is that we're importing DAG from Airflow, and this is written all in Python. So here we have default args for now. These are pretty standard. One of the important things, though, is the actual creation of the DAG object. So here we'll name our DAG. This would be ML-Expert DAG, and we would have a description of the DAG. So we're aggregating and joining interaction data from the search and carousel, and then we're joining that data with cancellation data, which is our label. We want to schedule this to occur every single day. So here we have a time delta and days equals 1. That just means that this job will run every day. Here we have the start date. This will be the first scheduled day in which the job will run. And now that our DAG is defined, we have to begin adding tasks to the DAG itself. Now, this first task here is actually an SSH operator. All we're doing is this code would actually execute in the worker of the Airflow instance that we have, and this worker would send this command to the name node of the Hadoop cluster, and the name node of the Hadoop cluster would be the one to actually run this file itself. First, we aggregate the search data, then we aggregate the carousel data, and finally we want to join the search and carousel data with the cancellation data. So how do we do that? Well, we simply Spark submit another job, and now we have to assign which order these tasks should happen in terms of this DAG. So here is where we do that. This may look a little bit strange, but all it's saying is that task 1 and task 2 can be done in parallel, and then after both of those are done in parallel, that will feed into task 3. If we go back and look at the graph view of this DAG, we can see that's exactly what's happening here. So we have these two in parallel, and those both lead into this join here, and that's represented by this code here. So what are some other things that we can do with Airflow? Well, as we talked about, if we go back to the DAG section, we can trigger the DAG, we can tree view, graph view, everything that we've seen before. We can look at how long each task has taken in the past. Here we'll typically have the recent task runs. We can see the in progress runs, what has failed, what hasn't failed, and we can refresh the DAG. So let's say that we upload a new file to S3. If we click refresh here, it will update the DAG itself. We can even delete the DAG, and that's mainly what we'll be doing in terms of DAG will just be these operations here. Now, administratively, we can go and look at the connections that we have set up. So if we scroll down to the connection, we have an SSH default connection, and that's going to be attached to our name node of our Hadoop cluster. So when we saw in our code SSH operator, how it knows to connect to our name node is because we have this connection configuration here. Finally, we can also manage the security of Airflow, so we can list all the users, all the roles, and assign permissions to which users can and cannot execute particular DAGs. So in total, for data processing, we can have jobs run periodically, say for instance every 24 hours. As well, if we use Airflow, we can create DAGs to help manage our data dependencies. And finally, if we use Airflow, we can scale up to support potentially thousands of scheduled jobs. That wraps up the processing orchestration video of the large-scale machine learning section of ML Expert. Thanks for joining, and we'll see you next time.